Hello! We are continuing our study of mechanical motion, and today we will look at such a topic as graphical representation of motion. Why is it necessary to describe motion using graphs? But first of all, it is convenience. It is a visual representation of motion, when we can use a graph to show how this or that body moves. With the help of a graph, we can solve many problems, and sometimes it is the graphical solution that is much more convenient than the analytical one. Let's see how a graph of some motion will look like. To do this, you and I must draw the coordinate axes. The vertical axis will show us the position of the body, and the horizontal axis shows time. So as time goes on, if the position of the body changes, it's going to be a line will be drawn, which will have a different shape depending on what kind of motion we're talking about. Let's consider the simplest type of motion as an example. Motion with constant velocity. Accordingly, motion with constant speed will tell us what? In equal time intervals, the body will travel the same distance. So the line that corresponds to this motion, it will have a constant slope. So what we can do is we can mark off the points on which this line could be drawn. That is equal intervals of time we have marked. It can be intervals of 1 second, 1 minute, or 1 hour, it does not matter. And so what we've got here is that we've noted equal paths that the body takes. So it can be, let's say, Ti, T2, T3, here we have Si, S2, and so on. And in this way, in a constant angle of inclination, we show that the motion is uniform, and the velocity in such motion also remains constant. That is, we determine this precisely by the angle of inclination of this graph. So we can write that if slope angle is a constant, then therefore the velocity will also be constant. Further, depending on what you and I are going to solve and what data we are going to pay attention to, of course, the graph can help solve different problems. That is, we see that there are certain points on the basis of which this graph was built, so we could mark them in this way. And with the help of coordinates of these points, we have drawn this line. But also such a graph can help us when we solve the problem of finding some additional data. For example, we need to determine how far a body has traveled for, let's say, this time interval. That is, it is between T1 and T2, and in this case we need to do what? We simply drop a vertical line on our graph of motion, and at the intersection we find the path that the body has traveled. That is, the graphical method of solution in this case helps us without calculations, immediately looking at the graph to find the value we need. This is quite convenient. But however, it is not always too accurate, because everything will depend, of course, on the format of the graph itself. But nevertheless, we can, even if approximately, but nevertheless estimate the answer of this task. So, next. The next point that helps to determine this graph is, of course, the calculation of the speed itself. That is, if you have a ready-made graph of motion, we can use it to find the speed itself. Let's see how this is done. So we have, again, conditionally a certain graph of motion. So let's say we have the position of the body in meters and the time in seconds. And there's some graph of motion at some particular speed. It is moving. How in this case we can determine the velocity of this body. To do that, we must remember that the velocity of the body will be called the ratio of the displacement of the body to the time for which the displacement was made. By displacement, we can understand some change in the coordinate of this body, that is its position, and also take into account the time interval during which this displacement was made. In order to understand how much the body has moved for a given time, let us mark 2 points on the graph arbitrary. And now accordingly we will show that this point had some coordinate at a moment of time, let us say t2. Here accordingly it is the moment of time t1. Here it is with coordinate x1, and here it is x2. Then it will turn out that the change in the coordinate of this body is the difference x2, x1, and the time interval that makes up this displacement is t2 minus t1. To show this on a graph, we can simply now extend this figure to a right triangle, and we can see that the change in the position of the body, it's this vertical cathetus dx and then the horizontal cathetus. Is the time for which this displacement was made. And thus, dividing this displacement by time, we get, respectively, the velocity of this object. Therefore, by any 2 points on this graph, we can determine, first of all, the velocity of this body, but at the same time we remember ourselves that the velocity of the body will also determine the angle of inclination of this graph. That is, if we want to find the velocity of a body using this triangle, we can determine the tangent of the angle of slope of this straight line. This tangent of slope will be numerically equal to the velocity of this body. This can be used to analyze graphs when we have several types of motion on one graph, for example. And we can see that the angle of slope of the graph changes. And so we can understand where and on what plot the velocity will be greater, where it may be less. Well, let's look at an example of such a graph. So position, time, and let's say we've got a body that's moving around like this. We see that here we have 4 plots on the graph. Let's say plot A, B, C, and D. And the question is, let's say, yes, we can analyze from the point of view that where our speed is higher, where our speed is lower, what generally happens to the body on each of these plots. And we see that for, let's say, plot A, we see what angle of inclination, right? For section B, this angle of inclination B will denote it. It's already smaller. We can already understand that the velocity at section B will be less than the velocity at section A. As for section C, here we see that there is no slope angle, that is this line. It is parallel to the time axis, and accordingly, we have no displacement between these points. So the velocity in this case will be 0. But if we talk about point D, in section D, then we see that here the angle of inclination will already be some gamma. But in this case, it can already matter. The tangent of this angle will be negative. It will say that this movement occurs in the opposite direction. The velocity will in this case also have a minus sign. With the help of the graph, you can also very easily determine the average velocity. That is, we look at where the body started moving from and where it ended up. That is, we can easily define the displacement of a given body as the difference between the final coordinate and the initial coordinate, and accordingly, if we know the time of this motion, we can find the velocity of the body. To find the traveling velocity average, we must also calculate how much of the total distance traveled by a given body and divide that by the time of the total motion. We can visualize this motion as the motion of some point along a straight line, and we can see that this motion will occur at different speeds. Let's demonstrate this. These parallel vertical lines will show what happened at each time interval. I mean, with these dotted lines. We're going to divide the entire movement into several sections. So, what happens in the first segment? The body moves with some velocity v1. That is, at this segment we know the velocity, and we can also determine it by knowing the displacement and time of this body, the time of motion of this body. Next, what happened on the plot v2? the velocity has already changed. That is, the body is moving at a lower velocity, but during the given time it will of course also travel a certain distance, and we can also determine the velocity by knowing the displacement and time of this body, the time of motion of this body. What happens at plot C? The body stands still. That is, in fact, there is a stop of this body, there is no movement, and when the body starts to move back, in this case we can show it by turning the velocity vector in the opposite direction. That is v3, it turns out. The velocity at the section D will be directed against the general motion, and the body eventually tries to return to the starting point. Of course, if we try to continue this graph, perhaps somewhere it will happen. With this graph, we show you that there are certain sections of motion that can be described in terms of coordinate. This is the first point. In terms of velocity, this is of course the second point. And so this motion will be more convenient and more visual if we can build graphs of this motion. That's the end of our lesson. Goodbye.